Welcome to example number 21. We have a circuit that involves resistors and a capacitor, known as an RC circuit. And at t equals 0, the switch is closed. We're asked to find the current immediately after it's been closed. And then finally, at the end, we want to know what the charge will be on the capacitor here. The capacitor is initially uncharged. At some initial time, t equals 0, we close the switch, completing the circuit and permitting current to loop around the loop and begin to charge the capacitor. We'll put the label of the voltage here. This is positive, negative. So here's a current going through here. We'll label that as I1. And then here through this resistor, we'll label that as I2. And then through here, through resistor 3, we'll label that as I3. Now, the initially at t equals 0, so right here at t equals 0, the capacitor is uncharged. And because it's uncharged, then the voltage across the capacitor is therefore 0. So essentially, there's no voltage drop across this resistor. So if it makes it easier to visualize, you could just imagine there's just like a wire going straight through there. That's not really what's happening, but there's no voltage drop across this. So you really have a resistor in series with this parallel connection of R2 and R3. So let's find the equivalent resistance of these three resistors so that we could find current 1. So adding these two resistors, you're going to get resistor 2, 3 is equivalent to 2 ohms. And then adding R2 and 3, that parallel connection of 2 ohms to the R1 in series with that, 8 and 2, will give you a total resistance of 8 ohms. And so now the total current will be the total EMF divided by the equivalent resistance, which gives you a current of 4 amps. And that current is really the current through resistor 1 because it's the same as the total current going through the battery. Now let's find the voltage across 2 or 3, that parallel part. So voltage 2 is the same thing as voltage 3, which is going to be the total current I, but through that resistance of 2 and 3. And that total current we found was 4 amps. And this equivalent resistance of this parallel connection was equal to 2 ohms. So this gives us a voltage drop of 8 volts across from, say, A here to B. And now we can find the individual currents of 2 and 3. And then I've found I2 by taking V2 over R2 to give you 1.3 amps. And then the same thing for I3. V3 over R3 gave me 2.7 amps. And as a check, 2.7 amps plus 1.3 amps gives you a total current of 4 amps. As you can see, this total current is splitting into these two pieces. Okay, now we've found the currents initially. So what we want to now do is find B, which is what would be the charge on the capacitor after it's been fully charged. And the initial charge of the capacitor was 0, but once it becomes fully charged, you'll have a voltage. So we need to use the capacitance of it, which is given as 4 microfarads, and multiply by the final voltage across this capacitor. So after a long time, the capacitor becomes fully charged, and this current I3 will decrease to 0, and the potential difference across the capacitor will be the same as the potential difference across R2. So hopefully you'll see that this current that goes through the battery will go through this resistor. When it gets to junction A, none of the current will go through here because it's fully charged. And so it'll go through B here, our resistor 2, and then continue around through the circuit like this. And there won't be any current through this section over here. And the voltage of the capacitor will be equal to the voltage across A to B, which is the voltage across resistor 2. Now, you can find the voltage across resistor 2 by taking the current I times resistance 2. Don't make the mistake of thinking that current is the current of 1.3 amps. That was what it was at t equals 0. Current after a long time will change because now the circuit will slowly change into just really having two resistors in series now only, because resistor 3 has no current through it and no voltage across it. So the equivalent resistance now after a long time will be just sum of R1 plus R2, which gives you an equivalent resistance of 14 ohms. And so now we can find the total current by taking the total EMF divided by the new equivalent resistance. The EMF is still the same battery, so that's a battery voltage of 40 volts, but now divided by 14 ohms. This gives you a current now of 2.86 amps. Now that you know the current that goes through the whole circuit, that's the same current through I2 and also I1. And so we now can find the voltage across the capacitor because we now know the total current and resistance too. That's going to be 2.86 amps multiplied by resistance 2, which is 6 ohms. So this tells you that the voltage of the capacitor is now 17.1 volts. And so now the charge across the capacitor on these two plates here will be the capacitance of 4 microfarads times 17.1 volts. And this will give you about 68.6 microfarads of positive charge on one plate and then negative 68.6 microfarads on the bottom plate. And that's it for this example.